Hi everyone, we're going to be looking at some questions involving circular motion. Some of them will be very straightforward, some of them will be a little bit harder. I will start first with question 1. It shows a girl that has a mass of 29 kilograms, so we need to make a note of that. Sitting on a playground roundabout. Her speed is, so this is a linear speed, remember, meters per second refers to linear speed. And then it asks you to calculate the centripetal force acting on her. If you look at the diagram, it also shows you that the girl is spinning from the pivot, so from the center of the circle. She sat at 1.2 meters, so the radius is 1.2 meters. So you know that you have to calculate the centripetal force. And if you look at your formula booklets, mv and r are related to F in this equation. You simply place the numbers in. Be careful not to forget the square power as well. So that will give you about 17 newtons. For part B, it says, what provides the centripetal force? Draw a free body diagram. Remember, a free body diagram is just a dot with only the forces acting on the object or person, not pairs of forces. And to label it with values with the three forces acting on the girl. You know that everyone has weight acting on them. Weight is mass times gravitational field strength, which is 29 times 9.81, just about 290 newtons. You also know that anyone that is sitting somewhere or standing somewhere will have an equal and opposite reaction, pushing them back upwards. This is not a reaction force, though. This is not a pair of forces. This is just two separate forces acting two different types of forces. We call this a normal contact force, which, since she's not moving up or down, should be equal to her weight. So if there is no resultant force in any direction, the person's not moving up or down. And then you have the centripetal force acting on the girl towards the center of the circle, which is 17 newtons. You already calculated that. Okay, so let's go to question 2. Okay, for the second question, it's talking about the weight of a person at the equator being different from the weight at the north and south pole. One of the reasons for the difference is the rotation of the Earth. This is actually true. If this is the Earth and this is the North Pole, this is the South Pole, let's assume that the axis of rotation is a straight line, even though in reality it's diagonal a little bit, but anyway, so the Earth rotates around its own axis of rotation. So when you are at the North Pole and at the South Pole, there wouldn't really be a centripetal force required. But if you're at the equator now, so somewhere around the equator here, then you do have a centripetal force acting because it's spinning. So you're at the very end of the radius of the Earth, let's say. Hence, you are experiencing centripetal force. But when you are at the North and South Pole, it's not spinning. Those parts are not spinning. They just stay stationary because it's spinning around its own axis. So then at those points, you will experience no centripetal force. Now it says calculate the change in measured weight caused. So the change in the measured weight caused by the rotation. Take the radius of the Earth. So the radius of the Earth will be, so for 2a, 6.4 times 10 to the 6 meters. The mass of the person will be 70 kilograms. And 1 day, so the period, that means 1 day means how long it takes. So it takes 1 day for the Earth to rotate about its own axis, and hence that's the period. So it takes it 1 day to 24 hours or 8.64 times 10 to the 4 seconds to complete a full rotation about its axis. So I have a lot of numbers, and I need to calculate the change in the measured weight. So to be able to understand how to get to that point is if you have a person standing here, there is a centripetal force acting towards the center of the Earth. But as a person standing there, let's say this is a person standing there, the person has weight and normal contact force acting on them, which, if you subtract from each other, should give you the centripetal force, which should always be directed towards the center of the Earth. So in other words, what you have is a general expression that centripetal force is equal to the weight minus the normal contact force. So what we are trying to calculate is the centripetal force. We know that centripetal force is equal to mv squared over r. We do have all the values nearly. We need to just use, instead of v first, we need to use that v is equal to omega r. We know that omega is 2 pi over tr. So I'll just simply place the values in. So it will be F is equal to, so basically centripetal force is the change in weight that will be experienced. Because at the north and south pole, the weight is actually just their weight. It will be mg. So let's just go through this quickly. We also have m omega squared r. So I thought I'll use this equation instead. So what you have is mass times 2 pi over t squared times r. When you place all the values in there, it will be, will come out to 70 times, this whole expression will be about 3.38 times 10 to the minus 2. So then we end up with 2.4 newtons. So if I go back to the original equation I wrote, so I wrote centripetal force, but this is the answer. You don't need to do anything extra, but I just wanted to explain it. If that's the expression for the centripetal force is equal to the weight minus the normal contact force, the reading on the actual scale will give me the normal contact force, because that's what it will be measuring. So what I will have is the centripetal force, the normal contact force is equal to the weight minus the centripetal force. The normal contact force is what will be giving me the reading on the scale, and that will be N is equal to the weight, which is 70 times 9.81, minus the 2.4, so by how much less it will be. And you should get something smaller than, obviously, 700 newtons, if you were asked that question. Then for part B, it says, is the person's measure weight greater at the equator or at the North Pole? And explain your answer. For this one, you have to state that the weight will be lower at the equator, because in a way, well, actually you can explain it with the equation we showed, that the weight minus the normal contact force, so you can draw this diagram, show that the centripetal force is equal to weight minus normal contact force, which means that the gravitational force is kind of being cancelled out by the centripetal force acting towards it. So the normal contact force will always be less than your weight because you're accelerating towards the Earth. It's quite tiny though. You can see 2.4 newtons is nothing, and if you divide that to get it in terms of mass, that will be, we divide that by 10, so it will be like not even half a kilo. So yeah. So it's lower at the equator because the normal contact force is what the reading is shown on the scale, and is weight minus centripetal force. So weight, as you can see, if you subtract something from it, it gets less. Okay, so for question 3, it's quite simple, the first part as well. It tells you I have a cyclist pedaling around a corner, tells you the radius, it tells you the speed and the mass, and to calculate the resultant force, which means the centripetal force in another way, because she's moving in around the corner, right, in a circular arc. So that's mv squared over r. You simply place the values in for what you're given, and you get 190 newtons. Then the question is asking, when going around the corner, the cyclist leans inwards towards the center of the curve. That's very important. Why is this? Draw a free body diagram for the cyclist and bicycle showing the forces acting on them to illustrate your answer. So once again, a free body diagram is simply all the forces acting on the object or person. What you have is a person that's driving, so if that's the cyclist, there's a bicycle. Don't laugh at my drawings. If the person leans inwards, that means that you'll have a force like this and the weight. So that's the normal contact force. Obviously, we know that normal contact force, if she's leaning forward, it will have 2 components. So this will be the vertical component, or and y, and this will be the horizontal component, or and x. So these are the forces acting on the cyclist. Let's go to question 4. This is a mass of 200 grams. So let's write that down. I need to change 200 grams to kilograms. It's tied to the end of a string with a length of 0.99 meters, so that one pass of its swing is almost exactly 1 second. That means the period is 1 second. Okay, one pass of its swing, that's what it means. The mass is pulled sideways until it's in a vertical height of 5 centimeters above its rest position. The mass is released, calculate the instant that the mass is at the lowest point of its swing. So if we're moving something vertically, so the radius, the radius is 0.99 meters, because if you have a length, a string, that's got something hanging off it, and you're spinning it. If the length is that much, if you're spinning it around, then that's the radius of the circle. So what we have to do here, this part links, in order to be able to calculate the speed, we're going to have to link the fact that it's above the ground, so it's got different energies taking place. Otherwise, it will be hard to calculate the speed at its lowest point of its swing. So when it's at its lowest point of the swing, it's got highest kinetic energy, and at the highest point of its swing, it's got the most potential, gravitational potential energy. So we're assuming that all of that energy goes from gravitational potential energy to kinetic energy at the bottom of its swing, without any resistive forces. Basically, there was no air resistance or friction. So we're making an assumption that GP, all the energy in the gravitational potential store goes into the kinetic energy store, so they should be equal. It also tells us that the mass is pulled sideways until its vertical height of 5 centimeters above its rest position. So it gives us a hint as to the change in height, So what we have here is mgh is equal to half mv squared. We just cancel the m's out because it's the same thing. Is 2gh square root is equal to v. This is a very important equation. You will see this constantly in terms of motion and energy changes. Many people don't realize that you can always refer back to this equation to calculate speed at any point. Especially when it's clear cut that one energy store will be, all the energy will be transferred to another energy store, and you can equate them and calculate them. So the speed will come about 0.99 meters per second. And then you are asked to calculate its acceleration. Now in this case, because we have circular motion, the acceleration would be A is equal to V squared over R. We already calculated this to be 0.99 for the speed, and the R radius is that much, so we cancel that out, so that should be 0.99 meters per second squared. And then you have to calculate the tension in the spring. Now, the idea is that you need to make sure that at the bottom of its swing, you know exactly what's taking place, right? So if this is my circular motion that it moves through, and this is the string with the mass. So I have two forces acting on the mass at the lowest point of its swing. One of them is the weight, which is mg, and the second one is the tension of the string. Now remember, if anything is to move in a circular motion, it needs to have a resultant force towards the center. So in other words, tension needs to be bigger than weight for it to be able to continue moving in a circular motion. So the centripetal force should be equal to the tension minus the weight. So if I rearrange this equation, I will get to calculate the resultant, to calculate tension, right? So yeah, I need to calculate tension. So if I want to calculate tension, then I simply take the weight to the other side, I add it, and tension is the centripetal force plus the weight. So mv squared over r plus the weight is equal to tension. That gives 2.2 newtons. Let's go to question 5. The hammer thrown in athletic events consists of a 7.3 kilogram metal ball at one end of a 1.2 meter of strong wire cable, so that's the radius. So the other end of the cable is a handle. To increase the speed of the ball before release, the athlete whirls it around his body on the end of the wire, as shown in figure 7. So he's moving in circular motion. So we straight away know that we need to analyze circular motion. The radius of this one is approximately 2 meters. Okay, so that was not the radius, that was just the length of it. A good hammer thrower can release the ball at 25 meters per second. Estimate the pull on the athlete's arm just before releasing the hammer. So here we need to use F is equal to mv squared over r to find the centripetal force. So the ball is 7.3 kilograms. That's exactly what's pulling on the person's arm. So the tension is one of the actions, the line of action only, that's holding it. Weight is not in the same line of action, so it won't affect anything, but the mass does have an effect on the centripetal force. So that will be times 25 squared divided by radius of 2, which gives you about 2,300 newtons. That's question 5 done. It was quite simple so far. Question 6. The curved banking of the cycle racing track in the velodrome is carefully designed. So it says shows it in figure 8. So just move the picture here so we can see it clearly. So the curving Shows a cyclist traveling a horizontal circle on a banked section of the track at angle theta. It doesn't clearly show. Oh, there's a theta angle there. Okay. The combined weight of the cycle on the right is W. The force at right angle to the track that the tracks exist on the cycle is R. So this is the normal contact force. Oh. Normal contact force. That's weight. It says the dotted line shows the line of action of the resultant force. In some questions that won't be given to you. So in other words, you might be shown the cyclist but not given the forces. So you have to identify that the force is always towards the center. The normal contact force is at the banked surface is obviously in the same direction, perpendicular to the surface of a person or an object. And it's asking you to show that weight is equal to R cos theta. Now what you need to do for this is that you need, if you prefer to redraw the diagram, you can. So this is going to be Rx and this Ry. So what's trying to tell you is that you need to show that weight is equal to the Y component of the normal contact force. So you have to resolve your forces, because remember, when we're dealing with forces, if an object has equal and opposite forces, or even a component of a force in the opposite direction, if it's not moving up or down, they have to be equal. But since we also have centripetal acceleration, we also have this force that provides it, since there's no other forces on the opposite direction. Anyway, so that will be basically what I'm trying to prove. Now the problem is, where does that angle theta go to? Okay, so if this is angle theta, this will be my angle theta. So if I redraw this as a triangle, it will be adjacent over hypotenuse, so that's cos theta is equal to adjacent, which is Ry over R, so Ry, so the component of R in the Y direction is R cos theta. Now part B is actually a really nice part, because you can use that for conical movement as well, which I'll go into another video when we do exam questions again. So in this case, it's telling you to use A to show that tan theta is V squared over GR, where V is the cyclist speed and R is the radius of the curve. Now we analyzed the vertical component of the normal contact force. Now we need to look at the horizontal component. We already used this triangle here. So I need to find out this component, which is Rx. So that will be opposite over hypotenuse, which is sine theta, is Rx over R, Rx over R. So now I'm confusing myself. So that means that Rx is R times sine theta. Since I have two expressions now, I have this expression and this expression, I know that tan theta can be calculated using sine theta divided by cos theta. This is a thing that you must have learned in maths so far. So if I divide the two expressions, that means I can get rid of the normal contact force if I don't have it, if I'm not given it to calculate it. So if I do Rx is equal to R sine theta over R cos theta, which is the Ry, this cancel, and I'm left with tan theta. We know that Rx, so this component of the normal contact force, is the one that's providing the centripetal force. So Rx should be equal to mv squared over R. Sorry, it gave us R as a lowercase, it says there. So I need to correct that. So mv squared over R is Rx, and we also know that Ry is the force that is the component that counteracts the weight. So it's the same, it's equal to weight, which is equal to mg. So if I write down this expression again, Rx over Ry is equal to mv squared over R divided by mg. Cancel out the masses. It's left with v squared over rg. So I have two expressions of Rx over Ry, which is tan theta is equal to v squared over rg. It looks a little bit messy, so I'll just quickly re-summarize what we did here. We broke down these are the forces that were acting on the cyclist. We broke it down into its components. We called this y because it's in the y direction, Rx for this one. Now Rx is the only force that provides centripetal force, so it's the resultant towards the center. Ry is equal to the weight because it doesn't move up or down. So we have these two expressions, and then we also use the angle theta to come up with the expressions in terms of angle for Ry and Rx. And we kind of equated them, we divided them to get tan theta. And then we used the Rx and Ry expressions to come up to the final answer. For C says for a velodrome with banked track of radius 35 meters, calculate the angle theta of the banking for the cyclist riding at 15 meters per second. So this one, you simply had to use the equation that you had to prove in this part. So it would be tan theta is equal to v squared over rg. And you just place the numbers in, 15 squared divided by 9.81 times 35, which is equal to, you need to do shift tan theta. So tan will be, the angle will be 33 degrees. For D, it says for a value of weight equal to 785, calculate R. In this case, it's actually quite simple because we know that Ry is equal to the weight, and we also know that Ry is equal, which we proved in part A, is equal to R cos theta. So in other words, weight is equal to R cos theta. So if you rearrange for R, it's equal to weight cos theta, which is 785 divided by cos 33, which is equal to 940 newtons. So you can see circular motion is a simple topic. However, you need to remember your basics from module 3, which has to do with analyzing forces and then identifying what the resultant force is towards the center, knowing how to analyze angles in terms of SOHCAHTOA, and then what we did here when we divided sine theta by cos theta to get tan. Let's go to question 7, which is the last one for this. In the Whirling bang experiment to verify the formula of centripetal acceleration, it is difficult to keep the string horizontal, and so the actual radius of the orbit is lower than the length of the string. Explain why this does not affect the results. So what it's asking us here, we can use mathematical equations to prove this, by the way. No one is saying explain just using words. Now we look at the whirling bag experiment. So what it's saying is that if the string is not perfectly horizontal, so you're supposed to be swerving it around and the string to be perfectly horizontal, but it's not, it's always at an angle. Because it's very, very hard to keep it in the horizontal actually. So what it's telling us is that to explain why this won't affect the results if it's at an angle theta. So what we have is the tx component. Once again, that's adjacent over hypotenuse. So that's cos theta is equal to tx over t. So that component can be calculated using this equation. The same actually applies for even the length of the string. So if this is the length of the string and it's at an angle theta, then we do need the component of the length that's on this direction. So that will be Lx is L cos theta for the radius. So we're talking about this being the radius, okay? So F is equal to mv squared over r. What you have is T cos theta, so that's my force, that's my centripetal force, is equal to mv squared over L cos theta, which cancels out.